Hello everyone, I'm Dr. Colin Seaton and I am at the University of Bradford, and this lecture I'm going to talk about co-crystals and investigating consistency of bonding and features across families of co-crystal materials. So multi-component crystals, both co-crystals and salts, are heavily studied as a way to modify the physical properties of APIs, improve solubility, tableting, etc. And while we've got the point where we've demonstrated the ability to make these, and there are numbers of studies on random selection of co-formers to create new materials, there's still a lot of work to be done on how do we, select the perfect co-former to give us the properties we want. Are there correlations between chemical structure of the components and the final physical properties of the material? Are there, what does the competition between the different supramolecular synthons entail? Does the choice of synthon have a direct effect on the physical chemical properties? Another thing that doesn't get quite so much study is the choice of composition. So a lot of the materials generally are done as 1-to-1 ratios, but if it's possible to make a 2-to-1, 1-to-2, or some other composition, does that give us superior properties, superior behavior? And the great kind of goal will be that could we possibly design and predict these things before making them? So there's a lot of interest in developing computational methods to predict crystal structures. A lot of the focus has been on polymorphism and being able to predict multiple crystal structures for a given molecule. And in principle, these methods can work just as well for co-crystals and salts. The challenges, of course, are we're adding multiple molecules into the system. We're doubling up the difficulties. And single component polymorphs are still quite time consuming to calculate. To do really accurate energy calculations, we're looking at months of cluster computer time. And there's always the problem that at the moment, our lattice energies we calculate even by DFT quantum methods still have errors around the 2 to 5 kilojoules per mole. And so our errors in our energies are still around sort of differences in the rankings of the crystal structure for polymorphic forms. And so we're adding that kind of challenge to kind of successfully rank and identify materials. So in terms of accelerating the process, are there ways of looking at, components and fragments of the materials and predict that rather than trying to do the whole crystal structure? Can we narrow it down to specific interactions? And indeed, if we look into lattice energies on multi-component crystals, very often the strongest interaction present is the one between the two different species, and that's contributing significantly to the overall lattice energy. So, rather than calculating the whole lattice energy, do we just need to look at one or two dominant strength interactions to push forward the predictive method, etc.? Okay, so what I'm planning to look at is a set of family of co-crystals and salts for some standard co-former materials. So isonicotinamide and nicotinamide are extensively used. And we have over 215 isonicotinamide structures in the CSD database. We have 158 nicotinamide ones. So they now start to give us that kind of scale of examples to see if we can find patterns in behavior in the system. The other advantage in this study is that they are a limited set of possible hydrogen bonding sites. So our studies of competition, we've narrowed it down to only really two. So we've got the nitrogen in the pyridine ring can accept acids and hydroxyl groups and other hydrogen bond donors. Our amide group can donate and accept together. And the other nice thing is that we've got the same groups, but we have them in different geometric arrangements. So there's a nice question about how does that affect the ability to pack and the sort of structures we can see out. So what I've looked at is compositional variation across these systems. Does that relate to the choice of functional groups present? Is there any predictability into the hydrogen bonding motifs we see or the crystal packing forms? Can we develop up a consistent structure? And is there any correlation between the energies of the material and the final product? Okay, so we start with the isonicotinamide materials. I've compiled together salts and co-crystals. If you separate them out, you actually get the same distribution of composition and the same behavior. So in these two cases, the relatively few salts that form aren't really behaving in any way different to the co-crystal systems. So we're going to treat them as all one set. And we see there's a limited range of compositions available. I mean, the vast majority are one-to-one, as we'd expect. And again, there is the question of whether this is because people aren't looking for higher compositions rather than the fact they don't exist. There's a balance that needs to be investigated. But if we take both the one-to-one and the one-to-two, I mean, that's nearly 80% of our of all the co-crystal systems in this case. So there are very few other compositions for isonicotinamide. It generally forms one-to-one or one-to-two. And if we we'll look later in terms of functional group, we'll see the high proportion of one-to-two for carboxylic acids is due very much to forming systems with dicarboxylic acids. If we go to nicotinamide, we generally see the same rough distribution. So again, one-to-one is most common. There's kind of an even split across the choices of functional group used to hold the things together. It does have an increase. So there's a reduction in the 1-to-2 and an increase in the other compositions. So one goes down by 7, one goes up by 7%. And so there does appear to be a trend in the nicotinamide that it will form systems with different compositions and lots of 3-component systems. So quite a lot of these are hydrates or solvates. And so that seems to start suggesting that those shift in geometry is making a molecular system that's slightly harder to pack together in the final structure. So there's less room to kind of include everything together. The other reason not to worry too much about the salt co-crystal split is that it's actually quite hard to uniquely define a system as either being a salt or co-crystal in some cases. So if we consider here 2-nitrobenzoic acid, there are 2 crystal structures in the CSD for it under different ref codes, because one exists as a salt pair and a co-crystal pair within the one crystal structure, the other is a full co-crystal structure. And so therefore, because there's a change in the chemical bonding, they're assigned different ref codes. But the only real difference between them is the salt form is a room temperature determination. The fully co-crystal form is 100 Kelvin temperature, so it's a low temperature structure. Now these have taken out an extract of the structure, and they look quite similar when you're just looking at local packing things. We're forming the same tetramer. They are linked by generally the same bonding. Now there are slight shifts and slight movements, and the salt form of the acid actually seems to tilt quite a lot on its position. And so these are different crystal structures. You can't overlay them. They don't match up beyond 2 or 3 molecules. So these are true kind of polymorphs of the system. And presumably, this is a temperature-dependent transfer of the protons. You heat it up, you're transferring it over to one side. Now, whether if you heat it further, do you get a higher temperature transfer and get it completely dissociating into a full salt form instead of this mixed system? We don't know. We just need to do some more work on that. So again, separating things out does require you to define your temperature conditions and other external experimental conditions. So there are things to remember when looking through the data. Also, the hydrogens are quite hard to locate in every crystal structure, and so it may be misassigned. So in the previous groupings, I assigned them by which functional group was hydrogen bonding into the isonicotinamide or the nicotinamide molecule. And so there's an interesting question of competition between different functional groups. If you have one that has both, say, a carboxylic acid and a hydroxyl, in principle, both of them could bind to the nitrogen in the pyridine ring. And so I've collected them here in terms of the group in bold is the one bonding to that nitrogen site. And so we see generally the acids win out. So the acids seem to be preferentially binding there over even other good hydrogen bonding functional groups, but there are still some anomalous cases. 4-hydroxy, no, not 4-hydroxy, 4-aminobenzoic acid forms an interesting 1-to-2 structure that has an NH pyridine interaction that's kind of rarely seen in other cases. But there's a kind of limit of all possible orientations and all possible combinations to investigate that. So if we start looking at hydrogen bonding patterns and motifs within the structure, we see again across the one-to-one systems. So we're looking entirely just the one-to-one systems. The isonicotinamide sets are much more predictable and reproducible than the nicotinamide sets. So the graph set here, the D2 is the link between the acid and the isonicotinamide. The R228 then is the isonicotinamide with another isonicotinamide. So you're forming a kind of dimer that then links through an amide-amide ring motif. And that's incredibly common for isonicotinamide. In fact, it's more common than it appears in this table because a lot of these systems here that I've labeled as D2, and they're built up entirely of just discrete hydrogen bonds under the analysis, are actually creating the amide-amide link. They're just forming from a Z'2 system, so they're not formally first level hydrogen bonds, they're second level motif. And so we find it's about 70% of the isonicotinamide systems have the same tetramer forming in the system. And the only other thing that appears is 12% will have the dimers linked, but they're forming some sort of chain motif through the structure. In contrast, the nicotinamide has only 36% forming that tetramer and a much higher 36% forming the chain. So there seems to be much less predictability in the nicotinamide system in terms of what sort of structural features. And the question is then, if we plot out these tetramers, so we see 72% time we have this, it's a lovely linear, flat structure. And so is it possibly just that that's much easier to pack in a crystal structure than the bent, distorted kind of zigzag pattern for the nicotinamide one? The nicotinamide also, I've not put it in here, there's an added level of complication because, of course, I've drawn it with the pyridine groups on opposite sides, but you could rotate around that amide bond and have them both pointing on the same side of the molecule. And again, there are examples of both of them in the system. Now, if we go back to that tetramer in the isonicotinamide, we find there is an even, similar level of switch. It's slightly more subtle. So if we look into them, 28% of them have the carbonyl group pointing on the same side of the molecule, whereas the majority, 72%, have the two carbonyls pointing in opposite directions. Now, if we calculate the energies of these two systems, we find that the kind of trans orientation is slightly more stable. It's about 2 kilojoules per mole lower in energy than this one. So there's an energetic reason to favor these structures over the other. But having those two different orientations has serious implications on the potential types of structures that the tetramers can build up. So when we have the cis one, where we have the carbonyls on the same side in the dimer, we find that almost all form this one-dimensional ladder through the crystal and have a large ring motif connecting them together. And so this is using up basically all our strong hydrogen bonds to form a single lattice structure. And that's credibly consistent in those cases. Therefore, that just leaves the challenge then of, can we predict which way round we'd expect to get this? What directs the formation? If you look at the trans geometries, we only find 3 general packing forms in these cases. So again, we've got our trimer. They are then linked through another ring motif, and it's the same hydrogen bonds that we saw in the previous one. They're just in a slightly different position due to the change in the relative positioning of the hydrogen bond donors and acceptors. So we've now got, again, a one-dimensional lattice structure formed from all the strong hydrogen bonding. If we continue searching through these trans ones, the other really common motif that takes up about half the structures is, instead of forming ring motifs, we rotate the molecules out of the plane and allow a chain form to come through. And now, because we've got more tetramers linked to each other, so the previous ones, we've got one above and one below, we've now got sets of 2 above, 2 below at different angles. This can start building up a 3-dimensional structure. And so the complete structure is all held together through strong hydrogen bonding. And the final set, which there are only 4 examples, is the use of an amide ladder motif, which again is rare for isonicotinamide, much more common for nicotinamide systems. Okay. So the question then is, if we've got these common one-dimensional motifs or a whole 3-dimensional structure, do we see that reproducibility in the co-crystal structures or the salt structures that we have? So for set 1, that transform, there is no isostructural crystal structures out there. So all the systems may have that same one-dimensional ladder, but packing that ladder into a crystal always results in a different form. So those weak interactions allow for a wide range of systems. Set 2 has slightly more predictability. So we find there are 3 sets of isostructural crystals. So these fluoro benzoic acids and nitrobenzoic acid are all the same crystal structure. You can overlay them on top of each other. This set is really interesting. So we've got a chirally pure acid and the racemic mixture of the same acid ends up with one being a Z'1 system and having a single, the enantiomeric form has the dimer generated up by an inversion center, whereas the enantiopure generates it up by making a Z'2 molecular system packing together. So there's some interesting kind of, the packings overriding the standard kind of crystallography, and then some more fluoride systems. But again, packing these ladders together seems to be quite a challenge to do it reproducibly. Set 3, however, once we've got that kind of 90-degree rotation and hydrogen bonding throughout the lattice, very much fixes the total packing. So 15 of the systems are completely isostructural, and they're all the ones that have them at 90-degree angles to the original tetramer. So if we can get that strong hydrogen bonding throughout the crystal, we start restricting the potential kind of crystal packing directionality, and we can start then controlling the crystal structure, and then hopefully changes in physical properties are then directly related to the chemical changes rather than the changes in the crystal packing. And there are 8 of them that don't quite get that 90-degree angle. They're slightly twisted out, and that ends up leading to kind of a helical ladder through the structure, which again, similar to the other ladder structures, much weaker forces prevent the packing of a directed system. And again, from the 4 that had the ladder, they split nicely into 2 sets of matching and not matching. So it appears to be we can limit the crystal forms, but only if we can somehow limit the interactions to be throughout the whole structure rather than kind of sheets and layers, and that balance of strong versus weak forces combining is an ongoing challenge. So let's then have a look at our energetics and how they relate to any physical properties. Now, the trouble is a lot of these studies, there are a lack of suitable physical properties measured, or we don't have structures for ones that have done, or finding a complete set where we're just changing one chemical component. In the isonicotinamide one-to-one systems, there's a complete set of increasing dicarboxylic acid length chains, and people have measured all the melting points. So in all of these, bar one, we all have acid to pyridine hydrogen bond, amide to amide, linking the dimers, so it forms an infinite chain, and then the chains are linked together through an NH to acid group. And if you do an energy framework calculation on it, these are the three strongest strongest interactions in the whole structure. So what I've done is I've taken the calculated energy for these three bonds, summed them together, and then plotted that out. That's the red line against the length of the aliphatic chain in the compound. The only one that differs is pimelic acid, which for some reason doesn't form the dimer. It forms the same two hydrogen bonds, but forms them to two separate molecules and forms these different kind of chain structures through the system. But again, that it's the same hydrogen bonds as that, so it sums up to something of a similar number. It is slightly less than the dimer would be. And so if we plot that against the melting point, we see an almost perfect kind of match mirror or plane. So we'd expect the ones with the strongest interactions to have the higher melting and so on. So we get a general trend that we increase the length of the chain, we reduce the strength of these interactions, and so we get a lowering of the melting point. We also see the oscillation between odd and even that we see in a lot of melting point data. We see that towards the end here, at least, in terms of the strength of the energy. Now, I don't know which way round. There are some issues over the N3, N4 systems. Either that N4 is not high enough in energy and should be down here, or the N3 is too high in energy and should be up there. But they're the only ones that don't quite fit in. The other issue is the succinic acid system. The literature has two melting points for it. The structure has been determined twice. The two papers have very different melting point values. So there are still some kind of issues on that, but it does seem to suggest just taking limited selections of what could be in the crystal structure is a possibility to understand physical properties. And again, we'd expect the melting points to be related to the solubility and so on. Another interesting question to look at when we're calculating these energies is, well, why are we getting those specific ones? That acid, the amide-amide interaction could be replaced by an acid-amide interaction. And indeed, if we calculate the energies of that, they are always higher, apart from the oxalic acid, than the isonicotinamide to isonicotinamide energy. So why aren't we getting the strongest possible interaction between the two? Again, the acid pyridine interaction will be lower in energy because it's only a single hydrogen bond, whereas an acid-amide one would be two. And so we'd expect it to come out higher anyway. And we see beyond the first and last one in this set, it's relatively consistent as you change the length to it. So why aren't we getting the hydrogen bonds we'd expect from purely kind of driven by the lowest energy system? And of course, what we've got to consider is not the formation of the dimer itself, but the motifs within the crystal. It's this tetramer. That's the consistent feature. And so if we form the tetramer, we're going to form two acid pyridine hydrogen bonds as well as that dimer in the middle. Now, we could consider breaking that up and forming two acid amine hydrogen bonds instead. Instead of having a dimer, or instead of having a tetramer, have two dimers forming. And if we calculate the energy difference between that system, we find the tetramer is about 26, 27 kilojoules per mole lower in energy than the one we don't see. So what these calculations seem to suggest is that when possible, we're going to go for the strongest ones. But if we can make 3 or 4 medium strength bonds rather than just 1 or 2 strong bonds, and we're going to always favor the more collective system that builds overall stronger energy. And so that adds a complication into predictive studies, because we don't want to then just optimize and find the lowest energy interaction. What we really need to find is the whole set of possible interactions and look at how they can all kind of pair up and combine with each other. Okay, so just to conclude, isonicotinamide seems to be much more consistent in terms of the types of bonding it shows, the types of features in the structure, significantly more limited range than nicotinamide. But there's no difference in terms of the energies. The energies is the same if you use either of them. And so I suspect this is more a geometric factor rather than an energetic factor. And again, we may get things that are higher in energy appearing in all the structures because they can combine together to make an overall lower energy, because you have multiple interactions rather than one or two. Okay, thank you very much for listening.